For the coordinate systems part of the lecture outline, you can click on the link that says Go to Coordinate Slides in the Frame slide. There are a couple of popular ways of specifying the location of a celestial object. The first is what you would probably use to point out a star to your friend, the altitude-azimuth system. The altitude of a star is how many degrees above the horizon it is, anywhere from 0 to 90 degrees. The azimuth of a star is how many degrees along the horizon it is, and corresponds to the compass direction. Instead of saying, look up about halfway up in the southeastern sky, you would say, look up 50 degrees altitude, 120 degrees azimuth. The altitude-azimuth system puts numbers to compass directions. This system depends on the observer's location and time. Since stars change their position with respect to your horizon throughout the night, their altitude-azimuth position changes. Also, observers at different locations looking at the same star at the same time will see it at a different altitude-azimuth position. Azimuth starts from exactly north equals 0 degrees azimuth and increases clockwise. Exactly east equals 90 degrees, exactly south equals 180 degrees, exactly west equals 270 degrees, and exactly north equals 360 degrees equals 0 degrees. For example, a star in the southwest would have an azimuth between 180 degrees and 270 degrees. Here's the sun's position in the altitude-azimuth system at different times of the year. During our spring and summer, the sun rises in the northeast, so the azimuth is somewhere between 0 and 90 degrees. For everywhere in the United States, the sun will cross the meridian, be up highest at local noon, when it is exactly south or 180 degrees azimuth. The celestial equator goes through the exact east, 90 degrees azimuth on the horizon, and exact west, 270 degrees azimuth. The altitude of the celestial equator where it crosses the meridian equals 90 minus your latitude. This means that during the spring and summer, the altitude of the sun at local noon is a number greater than 90 minus your latitude because the sun is above the celestial equator. During the fall and winter, the altitude of the sun at local noon is a number less than 90 minus your latitude because the sun is below the celestial equator. The second way of specifying the location of a celestial object is the equatorial coordinate system. This system is very similar to the longitude-latitude system used to specify positions on the Earth's surface. This system is fixed with respect to the stars, so unlike the altitude-azimuth system, a star's position does not depend on the observer's location or time. Because of this, astronomers prefer using this system. The lines on a map of the Earth that run north-south are lines of longitude, and when projected onto the sky, they become lines of right ascension. Because the stars were used to measure time, right ascension, or RA for short, is measured in terms of hours, minutes, and seconds instead of degrees, and increases in an easterly direction. For two stars 1 hour of RA apart, you will see one star cross your meridian 1 hour of time before the other. If the stars are not circumpolar, you will see one star rise 1 hour before the other. If they were 30 minutes of RA apart, you would see one rise half an hour before the other and cross your meridian half an hour before the other. 0 RA is where the sun crosses the celestial equator at the vernal equinox. The full 360 degrees of the Earth's rotation is broken up into 24 hours, so 1 hour of RA equals 15 degrees of rotation. The lines on a map of the Earth that run east-west, parallel to the equator, are lines of latitude, and when projected onto the sky, they become lines of declination. Like the latitude lines on Earth, declination, or dec for short, is measured in degrees away from the celestial equator. Positive degrees for objects north of the celestial equator and negative degrees for objects south of the celestial equator. Objects on the celestial equator are at 0 degrees declination. Objects halfway to the north celestial pole are plus 45 degrees dec. Objects at the north celestial pole are plus 90 degrees dec, and objects at the south celestial pole are minus 90 degrees dec. At the equinoxes, the sun is on the celestial equator, so it has a declination of 0 degrees. At the June solstice, the sun is at declination plus 23.5 degrees, And at the December solstice, the sun is at declination minus 23.5 degrees. This means that during our spring and summer, the sun's declination is positive, and during the fall and winter, the sun's declination is negative. Next slide. The gravity of the sun and moon pull on the Earth's bulge to try to reduce the tilt of the Earth's rotation axis. Like the slow wobble of a rapidly spinning top, the Earth responds to the gravitational tugs of the sun and moon by slowly wobbling its rotation axis with a period of 26,000 years. This effect is called precession. Precession causes the sun's vernal equinox point to slowly drift westward over time, so a star's RA and DEC will slowly change by about 1.4 degrees every century, a fact ignored by most astrologers, or about 1 minute increase in a star's RA every 20 years. Precession also means that which star we'll use to be our North Star changes over many centuries. When the Babylonians were the world power in 2000 BCE, the vernal equinox was in the constellation Aries, and the star Thuban, in Draco, was the closest bright star to the North Celestial Pole. At the time of Jesus Christ, the vernal equinox had shifted to the constellation Pisces, and the star Kochab, in the bowl of the Little Dipper, was the closest bright star to the North Celestial Pole. Now, the star Polaris is close to the North Celestial Pole, and the vernal equinox is close to the border between Pisces and Aquarius. In 2600 CE, it will officially be in Aquarius. In the year 10,000 CE, the bright star in the tail of Cygnus, Deneb, will be the pole star, and Vega in Lyra will get its turn by the year 14,000 CE.